welcome back. Let's start. Today we'll see a bit more of the theory of NP completeness, and from next class onwards we'll go into approximation algorithms. All right, so just to slightly recall where we were, we have this class NP. A problem A is NP complete if every problem in NP reduces to it. So the problems marked in yellow there, 3 coloring Hamiltonian cycle, TSP, I claim these problems are NP complete, meaning every problem in NP reduces to those problems. Okay? And what we did last class was we actually proved that circuit SAT is NP complete. Circuit SAT was this problem where the input is a circuit and you want to find an assignment that makes the output be 1. And we proved that this is NP complete, and in this proof actually I wanted to reduce any problem in NP into circuit SAT. And so that's what I tried to do. I tried to reduce any problem in NP to circuit SAT. And one thing I did during the process was, for concreteness, for exposition purpose, I said, let the problem be factorization. Okay, and so we saw a proof of how to reduce factorization to circuit SAT. But really the key thing which I wanted to convey is that the proof that factorization reduced to circuit SAT, if you look at the proof, you don't really use anything about factorization. In fact, the same proof shows that any problem in NP reduces to circuit SAT, and that's how we got that circuit SAT is NP complete. Factorization was just an example to keep things concrete instead of talking about an abstract problem A, but we could also have just talked about an abstract problem A. Okay, so that's one thing I wanted to clarify. The other thing I wanted to clarify was, okay, so now we have this particular problem, circuit SAT, which is NP complete, and then we started doing proofs of other problems being NP complete. So, in particular, the first thing we saw was 3-SAT is NP complete. Okay? We reduced circuit SAT to 3-SAT. I said 3-SAT is NP complete. So, there's one thing which why does this prove that 3-SAT is NP complete? Right, so if you want to say 3-SAT is NP complete, what we want to do is we want to prove that, of course, it's in NP. This is easy. And then we want to prove that every problem in NP, let's take any problem A in NP, you want to say that A reduces to 3-SAT. Okay? But we don't have to do this proof over again. We already know that circuit SAT is NP complete. We already know that every problem in, because circuit SAT is NP complete, we know that every problem in NP can be reduced to circuit SAT. Okay? So now you have this NP complete problem circuit SAT. If you just take this problem and reduce it to something else, if you just prove that circuit SAT reduces to 3-SAT, okay, if you just prove this, then you'll get that every problem in NP also reduces to 3-SAT. And this is because of this following simple fact. If you want, you can check out this and try to reason this through formally. But the simple fact is, if you have problem A reduces to B and B reduces to C, then A also reduces to C. So, since every problem reduces to circuit SAT, and now if you show circuit SAT reduces to 3-SAT, you'll get that every problem reduces to 3-SAT, and therefore 3-SAT is NP complete. So we don't have to work with every problem anymore. If you want to prove that some problem is NP complete, we just have to pick our favorite problem, which we know is already NP complete, and reduce it to that. Reduce from that. So prove that a problem A is NP complete, what you do is you pick your favorite NP complete problem, 3-SAT, independent set, the bunch of NP complete problems we'll see in the class, and then you prove that one of them reduces to A. So meaning A is harder than an NP complete problem. Okay? And then of course you need to also prove that A is in NP. These two together will prove that the problem is inside NP and harder than every problem in NP, so it's NP complete. Okay? So that's the strategy. So from now on today we'll see a few of these NP completeness reductions, and we will each time pick some problem which we know is NP complete and reduce it to another problem. Okay? Okay. Any questions on this so far? All right. Let's move on. All right. So let's. Okay. So at the end of last class, we were trying to prove this problem is NP complete. The problem is independent set. So independent set is the following problem. You're given a graph and an integer k. You want to find a set of vertices of size k such that no pair of them are connected to each other. They're an independent set. Okay? And we wanted to reduce 3-SAT to independent set. And by doing so, we'll prove that independent set is NP complete. Yes?
Clarify, is this maximum independent set?
Right. The question was, is this maximum independent set? No, actually, I'm here looking at a decision independent set. We're given a graph and an integer k. And you want to find an independent set of size exactly k. So it's a search question now. And it's easy to check. If you give a set, you can just look at the coordinate of the set. It should be k. And then there should be no edges within the set. Okay? Okay. And so we have a reduction from 3-SAT to independent set that we looked at last class. Let me just write it down. So what is the reduction? Well, you get a formula, 3-SAT formula on n variables and a bunch of clauses. So you get so you start with, so I'm going to describe the reduction. Reduction is basically, you're given a 3-SAT formula, phi with variables x1 through xn and clauses c1 through cm. Okay? Now I need to show how you construct a graph. I take this 3-SAT instance and convert it into a graph. So each clause, remember, is of the form, so let's just say C1 is, let's say, xi or not xj or xk. Okay, remember, and you have clauses and you want to satisfy all the clauses. You want to find an assignment satisfying all the clauses. Okay, you take the 3-SAT formula. What do? I'll just describe the graph in 2 steps. For every clause, if you have a clause xi or let's say xi or not xj or xk, something like this, you introduce a triangle. Introduce a triangle with vertices xi, not xj, vertices labeled xi, not xj, and xk. Okay, that's so that's one part of the graph. And then the second aspect of the graph construction is for all pairs of vertices labeled xi and not xi. For every pair of vertices that are negations of each other, add an edge between them. So that's what we did here. So we took the 3 clauses. For each clause, we introduced this green triangle there. And then for every pair of variables or vertices labeled by negations, we added an edge between them. So there's y to not y, and w to not w, and so on. And z to not z. So that's the graph. Okay, so that's how you convert a three-sat formula into a graph. I need to specify the size of the independent set I'm looking for. So I set the size of the independent set to be m, which is the number of clauses. So I'm looking for k equal to the number of clauses. Okay, so that's the reduction. Yes.
Why did you pick that value?
Oh, why did I pick k to be the number of clauses? It'll be clear as we describe the reduction. Any questions on this so far? So we just converted this three-set formula into this graph. Okay. So now, if you look at a satisfying assignment to this formula, I just wrote down a satisfying assignment here. In every clause, it would have one variable, at least one variable, which is 1. At least one variable. So I'm just going to mark every variable that's 1. So x is 1 here. In this clause, y and z are 0. In y bar is 1, z bar is 1, and w is 0. W bar is 0. Sorry, w bar is 0, t is 0, x is 1. Okay? So I just marked the literals that are 1. So actually I should specify this. A variable would be x1 through xn. There's some terminology, I guess, to be So when we say a variable, we just mean x1 through xn. Right? These are the variables. But a literal means x1 or x2, xn, or not x1, not xn. So every clause has 3 literals in it. Right? So that's important. Okay, so now, all right, so these are the literals that are true in this satisfying assignment. Note that this is, what I'm describing now is just our way to understand this reduction. Your reduction does not have access to a satisfying assignment. Right? That's important to remember. You should not use a satisfying assignment in the way you construct the graph. Because the whole point of the reduction is, I want to solve this 3-sat instance. I don't know the solution to this. We want to convert it into a graph. But this is just a way to, we're just describing what happens in the reduction. Okay, so this is the thing. All right, so then, so what is an independent set? And we want an independent set of size m. There are m triangles in this. So if there are 3 clauses, there are 3 triangles. Right? There are 3 triangles in this thing because there are 3 clauses. And if you want an independent set of size 3, you have to pick 1 variable from every triangle. You can't pick 2 variables from a triangle because they'll be neighbors. Right? You can never pick 2 variables from a triangle. Okay? There are 1 triangle per clause, and if you want exactly an independent set of size equal to the number of clauses, you have to pick 1 variable exactly from every clause. Okay? And so let's just do that. So let me describe the proof of the reduction. So in order to prove the reduction, I need to prove the following things. So suppose x1 through xn is a satisfying assignment. It's a satisfying assignment. Then I need to show you an independent set. So what is the independent set? Well, the independent set is going to be the following. It's just going to be in every clause there exists 1 true literal. Right? There exists at least 1 true literal. At least one thing is true in every clause because that's what it means to satisfy. it make sense? And so then you just pick some true literal in every clause. So then your independent set is pick any true literal in every triangle. Okay, so you would end up picking one vertex per triangle because every vertex has at least one, and you end up picking one. And this would be an independent set. Firstly, you don't pick two vertices from a triangle, so there are no edges between them. And you never pick xi and not xi. Right? You never pick y and not y. Why? Because only one of them can be true in a real assignment. So since you're starting with a real assignment, it will never be the case that both y and not y are true, and so you'll never pick two vertices that are negations of each other. So this would be an independent set. Okay? Does it make sense? Yes. Yes, thanks. Yeah, so one thing that we need to show in every reduction is that we need to prove that the reduction can be carried out in polynomial time. And that a lot of the times it's very clear from the reduction, because over here you see that it's basically a linear time reduction. Given the 3-sat formula, it's easy to construct this graph. It's basically in linear time. But in general, you would have to argue. But most of the cases, in most of the reduction that we see, it will be very clear that it's very easy to do the reduction. Okay, so that's one direction. The other direction is what we need to prove too, which is, what do we need to prove? We need to prove the following. Okay, actually maybe I'll use a new page. It's running out of space here. So the other direction is, suppose I give you an independent set. Whose size is equal to the number of clauses. You want to construct a satisfying assignment. Right? How do you construct this satisfying assignment? This is again sort of easy to see. Here's the idea. Well, the first observation is S contains one vertex from every triangle. Just because there are m triangles in all, and if you want to pick an independent set of size m, you have to pick one from every triangle. You can't pick two from any. So there should be one vertex in every triangle. Okay, some vertex in every triangle. So then you can define the satisfying assignment as follows. For each variable xi, okay, if a vertex labeled xi belongs to S, assign xi equal to true. Okay. On the other hand, if a vertex labeled not xi belongs to S, then assign xi equal to false. Okay, that's fine. But it could be that neither of this happen, because the set can pick any set of vertices. It doesn't have to, it could avoid this. If neither of these happen, assign xi. You could just assign it arbitrarily, but let's just assign it to be false or true, whatever. It doesn't matter. Arbitrarily, basically. Okay? So this is my assignment. And you can check that this is a satisfying assignment, because in every triangle, there is one vertex in the independent set. Right? In every triangle that we have, there's one vertex in the independent set. And what that means is, if you look at, let's say, the triangle XYZ, your independent set could pick any of the three vertices, but it will pick at least one. So you would end up setting at least one of them to be true. And your assignment will satisfy that clause. So because there's one vertex in every triangle, your assignment satisfies all the clauses. And the assignment is well defined because there's always an edge between a vertex labeled xi and a vertex labeled not xi. Therefore, you'd never be confused whether to assign xi to be true or false. Right? It cannot be that both xi and not xi belongs to the set S. Only one of them will belong. So this is a valid definition. So it gives you a valid satisfying assignment to the formula. So we proved in both directions that you can map the solutions. Any question? Yes. Right. So the question was, why is it true that there's at least one in every thing? The key thing is the following. So the size of the independent set is equal to the number of clauses. So there are m triangles in your graph, and the independent set has m vertices. So you can see that an independent set can't pick two vertices in the same triangle because they'll be connected to each other. So it has to pick one vertex in every triangle. So S has at least exactly one vertex in every triangle, and we are assigning the values xi based on S. So we'll end up putting at least one true label in every clause. Yes.
This will give us some satisfying assignment, right? It will not give the same satisfying assignment. It's not guaranteed.
Yes. So the question was, if you start with a satisfying assignment, get the independent set, and go back, you might not get back the same satisfying assignment. And the reductions that we talk about don't care about that. All it matters in our reductions is for every satisfying assignment here, there should be one there, and vice versa. So it doesn't have to be a bijection or inverses of each other. Yeah. Any questions? Yes. Yes, reduction need not preserve the number of satisfying assignments. And in fact, there's a special definition for reductions that preserve the number of satisfying assignments. I forget the name, but they are useful when you do reductions between problems that count the number of solutions. So there's an entire class called sharp P where the problem is to count the number of solutions. And if you want to do reductions there, you should preserve the number of solutions. But here we are doing it in NP, where you're just asking whether there's a solution. So the reductions are much simpler. Okay. All right. So let's. Is there any questions? All right. So let's continue. Okay. Let's see another. Let's see another easy reduction, and then we'll see a more substantial reduction. So here's going to be an easy one. But it's sort of an important one to know. So integer programming. What is this problem? Well, this is basically linear programming if you insist on the variables being integers. This is linear programming with variables forced to be integers. Okay. So let me formally define. What you have is your input is a set of linear constraints. Okay, it's inequalities, equalities, and inequalities and equalities. And your solution is, let's not do optimization. Let's just try to find a solution that satisfies the constraints. So a solution is just a integer assignment satisfying the constraints. So you can have x1 plus x2 greater than or equal to 5, x5 minus x6 less than or equal to 7, a bunch of constraints like this. and you just want to find an integer assignment that satisfies all these constraints, just like linear programming with integers. And also I took out the objective function because we want the problem to be in NP. We don't want to verify max or min or anything. But we can verify this, whether a solution satisfies all the constraints, you can verify it. So therefore, integer programming is in NP, as I've defined it. If I put in max or min, it won't be in NP. Okay? Is everything okay? This is a very, 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 natural problem to work with. It's also a really powerful problem that you could use, right? So, okay, so I want to prove that independent set is, integer programming is NP complete. Okay, that's what we want to prove. And in order to prove that integer programming is NP complete, I will just describe a reduction from independent set. Okay, we just saw that independent set is NP complete. We'll find a reduction to integer programming. And how do we do this? It's fairly simple. So you have a graph, right? So, and you want to find an independent set. You have a graph G equal to VE and an integer K. You want to map it to a set of linear constraints. Well, this is, like what you'd want is, we'd want xi, a variable, which is sort of 0 or 1, right? And it should indicate whether I, the vertex I, is in part of the independent set. Right, that's our intent. So, the reason I'm sort of marking this, in a different color is just that whenever we coming up with a reduction, there is an intent of what you want the variables to mean on the other side. But just because you have the intent doesn't mean the algorithm will respect your intent and actually do what you want. You have to actually prove that it follows the intent, right? So, like when we did the reduction from 3 set to independent set, we convert every clause to a triangle, hoping that it will pick one of the three, and so on. But the algorithm is just going to pick an independent set. You have to actually prove that it's forced to follow your intent. So, but in this case, it's going to be easy. But this is the intent. So, okay. So now, what constraints do we want to add? Well, the size of the independent set is k. That means that summation xi must be equal to k. Right? This is the size of the independent set. Okay? Okay, and the other constraint is these xi should be 0 or 1. So, okay? So, use this. And then finally, you have there should be no edges within the independent set. Meaning, if you have an edge, ij, if you have an edge ij, okay, you can't have both endpoints be equal to 1. Only one of them can be equal to 1. So for every edge ij, you can add a constraint of the form xi plus xj is less than or equal to 1 for all ij an edge. Okay. It's easy to generate this linear system given the graph. And if you find an integer solution to this linear system, you will have an independent set, because xi is forced to be an integer and in the range 0, 1, so it has to be 0 or 1. So all the xi's are 0 or 1, and then the sum of the xi's will be k, and they don't pick both endpoints on any edge because xi plus xj is less than or equal to 1. So therefore, this is a reduction. And it's easy to, in this case, it's easy to see that if you had an independent set, there's a solution to this LP, and backwards. If you had a solution to this LP, you get back the independent set. Okay. Any questions on this? So therefore, integer programming is NP complete. But you can see that integer programming is extremely powerful as an algorithmic tool, right? Because it's so easy to reduce anything to integer programming. Right? I didn't have to do much work at all. So in fact, using integer programming solvers is very, very useful because it's really easy to reduce any problem to integer programming. It's a very versatile problem, right? And so integer programming solvers are useful. Another strange fact that has happened is because 3SAT is somehow the mother of all NP-complete problems, or one of the first problems people prove is NP-complete, 3SAT solving has become one of the favorite things to do, and so we have very good 3SAT solvers. So if you have an NP-complete problem, which looks very strange, it's sometimes people find reductions to 3SAT and use a 3SAT solver. Just because our 3SAT has been hyper-optimized, right? 3SAT solving problem has been, there are contests where people solve 3SAT. So it's really, there's a lot of work on solving 3SAT, so you can use that. You can piggyback on that if you face an NP-complete problem. Of course, the same is true with integer programming. There are very, very sophisticated integer programming solvers, which works very well in practice. Okay, so let's move on. So, okay, so that's good. So this is an easy one. Let's look at something more tricky. So, okay. So let's look at this problem. It's basically the Rudrata cycle or the Hamiltonian cycle problem. Okay, what is a Hamiltonian cycle problem? You have a directed graph, and you want to find a cycle that visits every node exactly once. These two are important. It visits every node and exactly once. Okay? And it has to come back to the starting point. So here, let me see if I can recall the Hamilton cycle. Yeah, I just can't recall the Hamilton cycle. Okay, so there is a Hamiltonian cycle in this graph. It's basically a cycle that visits every node exactly once. I started by drawing that and adding edges, and now I can't recall where it is. But basically, you can see that it's a fairly intricate problem. I mean, it's one of the classic NP-complete problems. And now we'll see a proof that this Hamiltonian cycle problem is NP-complete. And we'll in fact reduce 3SAT to Hamiltonian cycle. Okay, we'll see a reduction which reduces 3SAT to Rudrata cycle. And so that will prove that Rudrata cycle is NP-complete. Okay, and we'll do it on directed graphs. Any questions so far? Is the plan clear? I want to take a 3SAT instance and convert it into a directed graph such that a Hamiltonian cycle gives me an assignment. Okay, so let's try to come up with this reduction. Right, so the key thing somehow when you're coming up with a reduction is, at a high level, what you're trying to do is mapping solutions to 3SAT to solutions to Hamiltonian cycle, Rudrata cycle. Okay? You sort of want to map 3SAT instances as solutions map to solutions in both directions. And so in order to do that, you sort of start by thinking about gadgets. What's the most basic object in a 3SAT instance? It's a variable, right? It's just a variable. So the most basic thing you would want to map is a variable. So if you just had x1, just a variable, okay, this variable, takes only two values. It only takes 0 or 1, right? So you would want something where there are only two kinds of solutions. You'd want a gadget or a piece of a graph where there are only two kinds of solutions because you want to map in both ways, right? And the graph that I've drawn looks like that. So look at this graph. Okay, suppose you want to go through every vertex in this graph and never visit the same vertex again. Right? You want to go through every vertex in this graph and don't visit anything again. How can you do it? Well, one obvious way to do it would be to go left to right. Okay? It visits everything once, never visiting anything twice. Or you could try right to left. Okay? There are two ways to traverse this without visiting anything twice. But there is no other way to go through this graph. Right? It's because if you start somewhere in the middle, you can go in one of the directions, but you'll miss out on all the other vertices. Right? So there's no other way to traverse this little graph such that you don't visit any vertex twice. Right? Question?
Do we not have to come back to this?
Right. So the question was right. So I'm just showing you a piece of a graph. We wanted a Hamiltonian cycle problem. Right. So if you want, well, of course, we'll use this piece in a bigger graph. But if you want to, the question is, why do we not have to come back to the original point? Let me just add this. Okay. Okay. So now. So now you have this little cycle. The key point which is important here is, actually this thing messes it up, so let's not do this. Let's not do this. But the key point I want to say is, this little piece has two ways to traverse it without visiting anything twice. Either you can go left to right, starting from one end, or right to left. You can't do anything else. Any other path will either skip some vertex or visit something twice. So that's nice, because that seems to be a way in which you can encode two possibilities. So let's say 0 means right to left, and 1 means left to right. Okay? And of course, always this whole thing is in yellow right now. It just means that it's the intended meaning. You're constructing the reduction, that's your intent. That, 0 should mean left to right, and 1 should mean right to left. Other way around. Sorry. Okay? All right. So now that is just one variable. Now you have n variables. What do you do? Well, here is a little graph. So I will have one of those gadgets for every one of the variables. I have n variables. I'll have n of these gadgets. Okay? And I need to traverse each one of them left to right or right to left. That's my satisfying assignment. So I need to add edges so that you can do it. So let me add edges so that you can do it. So I'm going to say, this is the starting vertex. Sorry. So for each of these paths, I add edges in both directions. So if I start from the top of this, if I start from S, and I want to go to T, right? And I want to visit every vertex. Let's even make it like a Hamiltonian cycle, okay? So if I want to start from S and go through every vertex in the graph, right? There's only a few, there are only a few ways to do it. I mean, true to the end, but there's only a few ways to do it in the sense that you have to traverse each of these rows either from left to right or right to left, right? That's sort of a gadget's restrictions. So you end up going right? You could traverse each of the rows either from left to right or right to left. You're free to do that. But then those are the only things you can do. If you do anything else, you'll skip a vertex and you'll miss out on the cycle. Right? So this graph has this property that if you look at its Hamiltonian cycles, there are 2 to the n different Hamiltonian cycles, or 2 to the n different Hamiltonian cycles, and they somehow correspond to 2 to the n different assignments. Because each row you can see whether the thing is going left to right or right to left. That in our encoding means x1 is true or false. Okay? So that's a key property. There are 2 to the n Hamiltonian cycles, and they correspond in some natural sense to encode 2 to the n different assignments. Okay? All right, so that's why you would look at this graph. Okay, so let's see. So far we haven't added any clauses in. We just figured out how to map the variables so that we get this. Now we need to add the clauses. We need to add the constraints. All right, so let's, this is our graph right now, and we want to add clauses. So here's how we add clauses. So again, the intended meaning is true is left to right, and false is right to left. Okay, that's our intended meaning. So let's say you have a clause x1 or x2, or not x2, or xn. Let me say x1 or not x2 or xn. Okay, this is a clause. Right, so we want to somehow create constraints for this class. So how do we create the constraints? We do the following. I'm going to introduce a variable, a vertex, a new vertex. This corresponds to that class. Okay? It's a new vertex that corresponds to this class. Let me give it a name. Let me call it C. Okay? Now I'm going to start connecting things. Well, basically what I want is, I want x1 to be left to right, x1 to be left to right, or x2 to be right to left, or xn to be left to right. That's what I want to force. I want to force one of these three to be true. Okay, that's our intended meaning. So I'll just do that. So I will, I'll add a detour from the x1's path like this. So what is the property of this detour? If you're going left to right, you can take this detour, visit the clause, and come back. If you're going left to right, you can visit this clause. However, if you're going from right to left, you cannot visit the clause. Right? You should look at the directions of the arrows that I drew closely. If I'm going left to right on that path, I can take the detour on the clause C and come back to the path. However, if I'm going right to left, I can't do that. Right? Look at just x1. x1, if I'm going this way, I can do this and come back. Okay? On the other hand, if I'm going this way, I can't take the detour. Okay? All right? So then what I'll do is on not x2, I want it to be right to left. I'll add arrows from x2 in the reverse direction. So let me add maybe green arrows, I guess. Okay, there are arrows, but they go in the reverse direction. So the way I have created the edges now, if you're walking x2 in the right to left direction, you can take this detour. But if you're going in the left to right direction, yes, you can't really take the detour. Okay, that's good. And for xn, I'll do the same, just in the, just precisely the same idea for x. Okay, so these are the only vertices, edges I'm going to add to this new clause. Okay, now what is your Hamiltonian path going to do? It has to cover every vertex in this graph. It has to cover, in particular, the new vertex that I added. It has to visit that clause. So it has to either walk x1 left to right, or it has to walk x2 right to left, or it has to walk xn left to right. It has to do one of these three things. Otherwise, it will not be able to cover the clause. Right? Yes.
So you will have one dot for every clause?
Yes. So now I created this for this clause. For every clause, I will have a new vertex. For every clause, I'll have a new vertex. I'll have m vertices. And I'll create these edges between these variable part to the clause part, just as so. So each of them forces some constraint on whether you're walking left to right or right to left on these paths. And that constraint precisely mirrors the 3-sat clause that you had. And that's why if you have a Hamiltonian cycle here, you can recover the 3-sat. And if you have a 3-sat in satisfying assignment, you can recover the Hamiltonian cycle. Yes, question? Okay, good question. So the question was, does it matter? Why did I draw these long paths for each of the variables? Does it really matter? It matters in that when I have many clauses, I don't want you to do lots of very, very spurious things of going from one clause to another clause and so on. So what I'll do is I'll actually create these long paths and keep the clause edges on these paths far away from each other. Meaning, look at the x1, right? X1, this corresponds to this clause, okay? But if there's some other clause here in which x1 participates, then maybe it's far away. The place where these clauses connect these variables, I want them to stay far away from each other or not really connect at the same point, because eventually, I'm not proving it right now formally, but we have to prove that, we have to argue that if you give me a Hamiltonian cycle, it has to look like a satisfying assignment. So I don't want too many confusing things in the Hamiltonian cycle. I want to force the Hamiltonian cycle to do very orderly things. In particular, there should be no way to go from one clause to another and things like that. So that's why I want to keep them separate. So I want these paths to be long. Just as long as the number of occurrences of the variable in the clauses. Yes? Right. So the question, the question was about the size of this graph. The size of this graph is, if you have n variables and m clauses, at most n times m, but it's even better because the length of these paths is just the number of occurrences of each variable. So you can basically get this to be order n plus m. It's linear, but for a reduction purpose, we don't even care so much right now. We just want it to be somewhat polynomial in n and m, the number of variables and number of clauses. Question?
So visiting all the clauses means we have a Hamiltonian cycle, and that makes up, and then we can deduce the satisfying assignment for the 3-sat problem.
Yeah.
Looking at that cycle.
Yes.
Which arrows you visited to go to that clause to create a satisfying assignment.
Yes. So the question is, how do you construct the satisfying assignment from the Hamiltonian cycle? And it's very easy. You just look at the Hamiltonian cycle and look at each of these paths. If you're going from left to right, it will be you mark it as true. If you're going from right to left, you mark it as false. And the way we have constructed this, it will satisfy all the assignments. Anything else? Any questions? Okay, so let me just I think I'll wrap up by just telling you the problems that I did not say, and there is a couple of easy reductions which I did not cover. I mean, it would be good exercise to even do it yourself. It's super easy, these reductions. Independent set to clique, right? It's just flip the graph, right? And then independent set to vertex cover, it's a complement. And then vertex cover to set cover, it's basically the same thing. Maybe I'll go through vertex cover to set cover because it has a simple idea which is useful. Okay, so I'll wrap up NP completeness maybe in the first 5 minutes of next class, and we'll talk about approximation algorithms.